Okay, let's look at the information that you should know for your whole entire unit. Right, we've had 3 tests, and this material covers at least 2 of them, but then our next video will cover the 3rd one. So let's pay attention to stuff that you may or may not remember. Okay, so here we have our graphs, and it says we have some zeros and some extrema. Okay, 0 is where it crosses the x-axis. Your extrema are your maxes and your mins, right? So B is an extrema, that's a maximum, local max. Here we have a local min at D. E would be your absolute maximum, right? That's the tallest y value. A would be your absolute minimum. And then this point C, that's our point of inflection. Right, the point of inflection are where the graph changes from concave down to concave up. So here our graph is concave down on this interval and then concave up from C to E. So let's see if we can answer some questions about the y values and the rates of change. From A to B, the y values are going up, so we can say that the y values are increasing. Our function is increasing because the y values are going up, right? So we had a 0 and then a 1, 2, 3. The y values are increasing, but at a decreasing rate. Okay, so we're talking about what are the y values doing and what are the rates. So the y values are going up, but they're not going up as fast, right? Because this is a concave down. And anytime we have a concave down graph, that's a decreasing rate. Concave down. So from A to B, the function is increasing at a decreasing rate. Okay? All right, from B to C, our function is decreasing, right? The y values are going down and also at a decreasing rate because our graph is concave down. Our y values are decreasing, they're going down, and our graph is concave down, so that's your decreasing rate. Okay, from C to D, our graph is still decreasing. The y values are still decreasing, but now our graph is concave up, so it's at an increasing rate. So the y values are still going down, but because it's concave up, the slopes of the line are now getting more and more positive. Okay, so the rate is talking about the slopes of your tangent lines. So our slope here is getting less and less negative, more and more towards 0. And then our last interval from D to E, right, our y values are once again increasing, and because we are concave up, it's increasing at an increasing rate. So know things about your y values, that's increasing and decreasing, and know things about your concavity, that's the rates. Concave down are decreasing rates, concave up at an increasing rate. Okay, our next one is this polynomial. So 2 things we need to know about polynomials. Number 1 is the sign of the polynomial, your leading coefficient. Okay, in this case we have a negative leading coefficient. That's a -2. And our power is a 5, which means we have an odd polynomial. Okay, so I expect you to know some things about the odd polynomials. So a negative odd basically looks like this. Okay? The end behavior is talking about what is the graph doing to the far right if it's increasing without bound, or to the far left. Okay, and we always wrote these as limit statements. So on the left, that's as x goes to -infinity. Okay, so on the left side, our arrow points up, which means our graph is going up to +infinity. Okay, so notice how your your x bound and your y bound are different because we have a negative odd function. And then our other limit statements, as x increases without bound, so as x goes to infinity, our arrow points down, so that means the limit is negative infinity. Okay, end behaviors. For end behavior of a polynomial, the answers are always infinities. Okay, the answers are always infinities for the end behavior of a polynomial, right? It's different if we're talking about a rational function, which we'll talk about later. But if it's a polynomial, your answers are infinities. So next we have an equation given to us in factored form. So when we have our factors, we set each of them equal to 0, and we can figure out where it crosses your x-axis, right? Your zeros. So this function has zeros at -2, at 0, so the origin, and then at +4. So this is where our graph is going to cross or touch your x-axis. Okay, and that happens based upon your multiplicity. So if we have an even multiplicity of 2, that means our graph is going to bounce, right? It's going to touch but not cross. And everywhere else, our graph is going to cross. So if we think about it, this is x, and this is an x squared, and this is an x. So we have a positive 4th degree equation, or positive x to the 4th. Okay? So it's going to cross at -2. It's going to cross at 0, and then it's going to bounce at +4, because that's where we have a multiplicity of 2. Okay, so here our limits are infinity. The left side our arrow goes up, the right side our arrow goes up. And we have 2 local minimums. We have a local minimum here and there, and we have 1 local max right in there. Okay, which means we have 2 points of inflection because our graph changes from concave down to concave up, and then again to concave up. Okay, so that's a pretty good thing about multiplicities and polynomials. Okay, our last one. The graph is shown. Label the extrema and inflection points. All right. This looks like it is a positive odd function. Right, we have the same, so as x goes to negative infinity, the limit goes to negative infinity, and as x goes to positive, the limit goes to positive. So if this is true, if your limits behave the same as your x values, then we have a positive odd function. Okay, so our extrema, right, our maxes and our mins. Here we have a maximum value at the top of our hill. Here we have another local maximum, right? So these are not absolutes, these are local maximums. So 2 local maxes. That means we have a minimum at the bottom, right? 2 local minimums. And in between a min and a max is where we find our points of inflection. So there we have an inflection between our max and our min. Here we have an inflection between your min and your max. And then we would have another inflection point between our next maximum and a minimum. Okay, so you always have an inflection point between 2 extrema. Between a max and a min, or between a min and a max, you're going to have a point of inflection. So this graph has 3 points of inflection. It has 2 local maxes, and it has 2 local minimums. Okay? So that is almost everything. We have one more question about Unit 1. Okay, your last question about our first unit test over functions and stuff, attributes, rates of change, and polynomials, is this chart here. So we have to do 2 things. Number 1, we look at the change in x, so our delta x. 0 to 1 is 1, so this has a constant change, right, in between our problems. So 0 to 1, 1 to 2, 2 to 3, 3 to 4. There is a constant rate of, a constant change, right, an equal distribution, maybe I'll say that, between your values. Okay, so now we're going to look at delta y over here. So from 1 to 2 is plus 1. From 2 to 5 is plus 3. From 5 to 10 is plus 5. From 10 to 17 is plus 7. So if we first look at our delta x over delta y, delta y over delta x, our rate of change, okay? So first we have 1 as your rate of change, 1 divided by 1, and then we have 3 divided by 1, and then we have 5 divided by 1, which is 5, 7 divided by 1. So notice your rates of change are not constant, right? We have a changing rate of change, which means this is not a linear function, not linear. But now, let's look at the rates of our rates of change. So from 1 to 3 is a change of 2. From 3 to 5 is a change of 2. From 5 to 7 is a change of 2. Okay? That means we have our rates of change are constant, which means we're looking at a quadratic style of a formula. Okay? Because the rates of change are constant. Okay, so if these were not constant, then we would look at their rates. And if we had 3 iterations, so first we have a linear. If these are the same, then it's a linear equation. If the rates are the same, that's a quadratic equation. But then if they were different, we would look at the third rates. Okay, and if it's the third rate, then that would be a cubic. Okay, so that was our information that you were tested over on our first unit test.